Welcome to this next part of the video. In this part, I am going to explain about the S matrix. So previously we had discussed about Z matrix, Y matrix, and what is a reciprocal network based on this Z and Y matrix. So today we'll discuss the scattering matrix, or also called as the S parameter or S matrix. So this is the widely accepted parameter for microwave network analysis. So let us see. So as I was saying that, as discussed in the previous lectures, that analyzing microwave networks with voltage and current is a very difficult task. So we have taken into the matrix, and in at high frequency direct measurement involve magnitude and phase of wave traveling in particular direction. So when the frequency really increases, then a small device can also create a phase difference issue while measuring with equipments, and hence using voltage and current method is not sufficient, because this Z and Y parameter obviously use the voltage and current method. So scattering matrix become accepted parameter to analyze the microwave networks, and it was more towards a direct measurement. So you can see here, this is one device which can directly measure the S matrix or the S parameter of any device under test. So first we'll see what is the S matrix and what does exactly it measures. So similar to your impedance matrix and admittance matrix of an input network that we have looked before. So this is your input network that we are looking into. So in the same one we'll be discussing the S matrix second. Scattering matrix provides us a complete description of the network. So we'll see how it gives that. Then we'll solve a problem as well to get some more knowledge on this. Then scattering matrix relates the voltage waves incident on the ports. Those are reflected from the ports. So this scattering matrix is only will be based on how much voltage is incident and how much voltage is reflected back from one particular port to another particular port. So basically it just compares the voltage, not no current is involved here, so it becomes easy to understand as well as measure also. Just the maximum voltage, how much maximum voltage was applied and how much maximum voltage was reflected or measured. So that's it. So scattering matrix can be calculated using network analysis techniques, and otherwise scattering parameters can be measured directly with a vector network analyzer. So this is what the device is, vector network analyzer, or widely known as VNA, and this is from a Agilent company called as programmable network analyzer, and this can work from 10 megahertz to 67 megahertz. So when frequency is high, then we have to define that on which frequency it can work, and this particular image is shown here, it can work from 10 megahertz to 67 gigahertz. Once the scattering parameters of the network is known, then conversion to other matrix can also be done, like S to Z matrix, Y matrix, or any other matrix can be done. So we have another matrix called as ABCD parameter as well. So all these conversions can be done, though it is not required at times. Only S parameter is enough, but there is a method that it can be done if else or if any case it is required. So what is scattering matrix and how it is defined? So we are using the same network here, the input network, where voltage incidence is there as V1 plus, current incident taken as VI1 plus, and the voltage reflected back is taken as V1 minus, and current reflected back is taken as minus I1 minus. Similarly for input also, Vn plus, In plus, and Vn minus, In minus, negative of In minus. So we are considering this kind of network here. Now what is S parameter? So the scattering matrix S is defined the relation to these incident and reflected voltage waves. So remember, here it is voltage waves only, nothing else, no current is involved here. So what is that? So V1 minus, okay, so if I just write one thing from here, so V1 minus means how much is reflected. What is the value? That is equals to how much incident voltage was there, means how much actually the signal was applied into the S matrix or the scattering matrix of this particular network. Okay, so this says that S11 is a factor which will decide that if V1 voltage is applied at port 1, then at same port 1 how much voltage is getting reflected. So ideally what? Ideally your reflection should be 0. In that case your S11 should be very low. Okay, so S11 is measured in terms of dB, we will see into that also. Similarly, if I say what is V2 minus, okay, V2 minus means how much voltage is going out of this network 2 when I am applying a voltage of V1. So that is equals to V1 plus into S21. So here it point is important to remember is 1 is the input and 2 is the output. That means how much you are applying V1 plus so that you are getting V2 minus. So how much you are giving the input here as V1 and with reflection of means with relation to S21 it will give you that how to V2 minus how much V2 minus is available at port 2. That means how much voltage is going out of the port 2. Similarly, all other ports can be related with effect of voltage by this matrix. Okay, so if I say now let's say V3, okay, we'll say V1 minus when the voltage is applied here. So how that can be written? So that is voltage applied here, that is V3 plus into S3, sorry, S13. So here I 3 is the input and your 1 is the how much means in which port we are going to measure the output voltage. Okay, so like this the matrix is done. So it is written as V minus is equals to S into V plus. That means how much voltage is outgoing from a port is equals to the related S parameter or this matrix into the how much voltage is applied on that particular port. So this is how the S matrix is actually defined. Now here important to understand is what? So this is defined as Sij is equals to Vi minus divided by Vj plus. So from where it is coming? So there is where it is coming. S11 equals to V1 minus then S11 equals to V1 minus divided by V1 plus, or here S21 is equals to V2 minus divided by V1 plus. So this thing is written here. So consider a specific element in the matrix where Sij is equals to Vi minus divided by Vj plus. Okay. So here first one at the top, second one at the bottom. So I and J, I and J. So in this case, what is J? So Sij is found by driving port J with an incident wave of Vj plus. That means driving port J means any port in the network is given as V plus from the port J. Okay. Then measuring the reflected wave amplitude Vi minus. Reflected wave amplitude, or it can be written as outward wave amplitude as Vi minus. Okay. Vi minus. So you are giving a input voltage of Vj V plus at some J network and you are measuring the output voltage V minus at some I network. Okay, and all other things are open circuited or matched load is there. So consider that there is nothing coming from there. So concept of matched load we will be discussing later. So this is the thing there. Now the waves on all ports except the J port are set to 0. So waves on all the port, that means if I am measuring this port 1 and port 2, then we consider that nothing is coming from all these ports. So nothing is there, that means no voltage is applied and these are matched loads. Matched load means there won't be any reflection internally so that no extra voltage is added. So the waves on all the ports except the jth port are set to 0. Why jth port set to 0? Because jth port is the node of consideration where we are giving the input port. And that is all other ports should be terminated with matched load to avoid any kind of reflection. So why the termination with matched load is required? So that will be discussed later. But the point is it should be matched, load should be connected there that so that there won't be any kind of reflection. So if any wave is here and if it is a wave, it is propagating everywhere, and if it gets reflected from here, then it can affect the output measurement. That is why match load, if it is connected, then there won't be any kind of reflection. That is why match load is taken. And with this condition, S11 gives the reflection coefficient of a port. Okay, so a reflection coefficient means what? So if I write S11, that means how much input voltage you are giving at V1 plus and how much you are getting at, so let's write it here. S11 means how much voltage is available at port 1 when you are giving a input of voltage at port 1. So input and the output relation at the same port gives the reflection coefficient. That means if you are applying a V1 plus voltage, then how much part is getting reflected. Okay, so ideally there should not be any reflection for ideal condition, so that should be the goal. That means this S value should be very low. Okay, so this is what it then, due to this SII, okay, the S11, S22, S33, like this, all these are called as the reflection coefficient, and Sij is called as the transmission coefficient. Why it is called the transmission coefficient? Because it says that from jth port to ith port how much voltage or how much signal is transmitted. So that is all about your S matrix. Now let us see one problem, that how you can find the S matrix. Okay, how to find the S matrix and reflection coefficient. So find the scattering parameter of the 3 dB attenuator as given in the circuit. So it says that it is a 3 dB attenuator circuit, called as a 3 dB attenuator circuit. Why it is called, we'll see. So what is S11 value? That is equals to V1 minus divided by V1 plus. Okay. Now V1 minus V1 plus, how to find that? So V1 minus divided by V1 plus is also equals to the reflection coefficient that we know from where? That we know from wave propagation. Okay. So that we know from the wave propagation. So if we know what is wave propagation, from there we can calculate what is the reflection value, what is the voltage incident, what is the voltage applied or reflected. So that is equals to Z in. So why this one is written? That means port 1. So Z in minus Z0 divided by Z in plus Z0. Okay, so S11 can be found as reflection coefficient seen at port 1 when port 2 is terminated in a matched load. So that is Z0 equals to 50 ohm. So why Z0 is equals to 50 ohm? That is also important to know. So here, see here. So Z in is equals to how much? Z in from port 1. If you look, then that is equals to these two are in parallel. So if 50 ohm is connected here, so 8 and 50 they will be in series and parallel with 141.8. Again this is in series with this one, so all the combination will give you as 50. Now in this case Z in minus Z0 divided by Z in plus Z0, so it will be 0. Why? Because this Z in value is coming as 50 here and the load is terminated with a 50 ohm. Actually it is given 50 ohm uh, termination is there. I forgot to write that point. In this case S11 is equals to 0. Okay, so that means it is ideal network where it is not nothing is getting reflected back. V1 minus is equals to V1, so here I can say V1 minus is equals to V1 plus into S11. So S11 is 0, that implies V1 minus is equals to 0. That means if you are applying a voltage V1 plus here, then the reflected voltage V1 minus is equals to 0. So that is what it means. So next is S22 also, because you can see network is very symmetric. If you look from either side, the network is same, so the calculation is going to remain same. Okay, so just remember what is this Z in. So Z in is, if you look from this side, then what is the total resistance of the circuit and when this is connected with a 50 ohm resistance. So that's what been done here. Okay, so S22 and S11 became 0. Now point is to find S21. So how to find S21? S21 is you are measuring the output at 2 and giving the input at port 1. That is why it is outward direction in V2 minus and inward voltage at V1 plus when V2 plus is equals to 0. That means nothing is coming from the port 2. Only only input is at port 1. In that case, port 2 is connected with a terminated with a 50 ohm resistance and no voltage is applied there. In this case, we have that V1 plus, okay, V1 plus is equals to V1 and V2 minus is equals to V2, okay. So V2 is equals to 0 now here. So if we apply the voltage at port 1 and using the voltage division rule, so we can find that V2 minus will be equals to 0.707 V1. So we should do the calculation that how this voltage divider rule is applied here. Another point is why this voltage divider rule has to be applied two times, because you are giving input at here. So V1 then it will be first voltage divider will be including this one, then whatever voltage is available here, then it will be applied here. So like this, 2 times voltage divider rule will be applied here. Okay, so you can see this 50, so this 50 and 8.56, so we'll get one voltage divider, one voltage dividing here. Again these two will be one voltage dividing 8.56 and 141.8. Okay. Again, from where this 41.4 is coming, so basically this is the parallel combination of 141.8 and your 8.56 and 50. So combination of this parallel with this. So the series parallel, if I go on explaining, it will take time, but this is how you will get the 0.707 value of the B1 input. So now why it is called as a 3 dB alternator, because if this is converted to dB, this comes as 3 dB. That means only 3 dB power, if 100% was given, then only 70% power is getting delivered at another port, and that is equivalent to your 3 dB of attenuation or reducing the power. Okay, so this is how you can find S21 as well, and when the network is symmetric, so S21 will be equals to S12. So next is this is calculated, and how this 41.44 came, that also I have written here. So it is parallel combination of 141.8 and 58.56. Okay, 141.8 and 58.56. So it is coming from here. 50 ohm is connected here. So this one and this one are in series. So parallel of that, it is coming as 41.44. So this effective becomes 41.44, and this one with this one voltage divider rule is applied. Okay, next S12 and S21 both are same. So if we consider what is the input power, so power is what, B square by 2Z in this case, so it is V1 plus divided by 2Z naught. So from where this is coming, from wave propagation equations. So this is the P input, and what is the P output power? So P output power is equals to V1 minus, because output power from here is V1 minus. So for applying a V1 plus in a power, then P output at the same port is V1 minus. Okay, so that is equals to, again, what is the value of V1 S21 into V1 plus. Okay, so like, sorry, this will be V2. So in this, if it is calculated, it will be coming as P in divided by 2, which is equals to your 3 dB. So hence it is called as a 3 dB attenuator circuit. So next is scattering matrix for a reciprocal network. It is symmetric if the network is reciprocal. That means if the network is like this from either side, if you look it same, then the condition will be S matrix is equals to S transpose, and it is a lossless network, or if the matrix is unitary, that means S transpose into S conjugate should be a unity matrix. Okay, in this case it is called as a lossless network. It has to follow this. So this is just written for that condition. So it will be delta ij, where delta ij equals to 1 if I equals to j, and delta ij equals to 0 for I not equals to j. It is also called as Kronecker delta symbol. Now this lossless condition is here. Okay, it has to be 1. So like unity matrix means what? It will be a diagonal matrix. All other values should be 0. So that's why this condition is written. So next we'll do another one. So determine the network is reciprocal and lossless or not. Then port 2 is terminated with a matched load. What is the return loss at port 1? Port 2 is terminated with a short circuit, and what is the return loss of port 1? Okay. So one is short circuit, one is matched load. We have to understand that first, and this is the network given. So it's a S parameter is a complex number. So it is the network is given like this. Now, because S is not symmetric, so network is not reciprocal. Why not symmetric? You can see here this transpose is not same, right? S is not equals to S transpose. That's why it is not symmetric. So first is it is not reciprocal, and for lossless the value should be unitary, which is not. So that is also it is not lossless. It is not unitary, that's why it is not lossless. So part A is done. So next we'll go to port 2 terminated with a match load. Okay. So port 2 is terminated with a matched load. If the matched load is there, then we can see the reflection coefficient S11 is 0.15. So from where it is coming? So this is 0.15, this is S11, the reflection coefficient. When port 2 is terminated with a matched load, then S11 value is like this. So return loss is how much? 20 log of the reflection coefficient, that is 16.5 dB. So the question is port 2 is terminated, what is the return loss? So return loss is calculated as 20 minus 20 log of the value. When port 2 is terminated with a short circuit, so see here, if port 2 is terminated with a short circuit, the reflection coefficient in port 1 can be found as, how to found? So we'll consider that V2 plus is equals to minus of V2 minus. That means I am considering that V2 minus is the negative means outward direction, V2 plus is the positive direction. So if I consider this V2 is nothing but negative of V2 minus, just opposite it. So we'll just consider this one, and then V1 minus is equals to how much? That is equals to S11. So from where this is coming, I'll just show you. So this is coming from this network. Okay, so what will be V1 minus is equals to S11 into V1 plus S12 into V2 plus, right? So that is what is been written here, S11 into V1 plus S12 into V2 plus. Now we have considered V2 plus is equals to minus of V2 minus, so that's why you can replace like this. Okay, then again, what is V2 minus? V2 minus is S21 into V1 plus. So how much input we are giving at port 1, how much power we are getting at port 2, and the S22 and to V2 plus. Okay, so again here V2 plus is replaced as minus V2 minus. So with variable separation method and all, we can find the value of V1 minus divided by V1 plus. Okay, so if all things we put here, so here only uh, V2 is this V2 value, if we can put here, so now the equation finally we can get something uh, V1 minus divided by V1 plus. If you take the ratio, then it becomes S11 minus S12 into V2 minus by V1 plus. So just putting this V2 minus value in this equation, so we'll be getting this. So all the values are known now. Okay, so if all the values are known now, now from where it is coming, S12 into V2 minus divided by V1 plus. So just putting the V2 minus by V1 plus, replacing all the values. So we'll be getting here, these values are given here in this S matrix of all the S parameters. Just putting the value, we can get what is the this V1 minus divided by V1 plus. Okay, so that means you are giving input at port 1, we will be getting output at port 2 if the port is short circuit. If it is match load, then we are getting this. If short circuit, we are getting this. Then the return loss will be taking the 20 log of this, so 6.9 dB will be the answer. Okay, so with this next we will see that what is generalized S parameters, means how do we generalize that. So the voltage and current on transmission line is represented in terms of incident reflected wave amplitudes. Okay, so V equals to total voltage at one port is equals to total inward voltage plus total outward voltage, and with the impedance term, so current will be 1 by Z0 into V0 plus minus V0 minus. That means total voltage available there. Okay, so total voltage magnitude is addition of that, and total current is difference of the voltage, how much actual potential is there, divided by the Z0. Now rearranging the above, we can get the incident reflected voltage in terms of total voltage and total current. So V0 equals to total voltage and total current. Okay, in this term where that is being written. So now if this is used to calculate what is the total power, then it comes as 1 by 2 real of Vi, that is a normal formula, and it comes a 1 by 2 Z naught. So V plus minus V0 minus, so in terms of the reflected and the incident voltages, and the average power delivered to the load can be PL. It is called as the average power delivered to the load PL. Okay, So the calculation is only valid when the characteristic impedance is real. Okay, this value, it has to be real. Generally, it is always real, and it is invalid when Z0 is complex, or that means the line is a lossy line. Means the network has the component which is lossy in nature. In that case, this calculation won't be possible. So so next is we can the incident and reflected power amplitudes can be represented as A and B, and the following linear transformation of the total voltage and current can be given here. So A equals to, this is the incident, so this incident is A, V plus ZRI divided by 2 root over of R, and where ZR is equals to RR plus JXI. This is the complex combination of the actual Z value. Okay. So in this case, the voltage can be given as ZR conjugate and ZRB divided. ZRB means what? This power. So this it's just a power and current relation is there. In that case, the total power delivered can be given as incident in terms of incident power and reflected power. It can be given as this. So if you need, just put a comment there. I will provide this PDFs to you. That's not a problem. Then the reflection coefficient is given in terms of the impedance as Rp is equals to B by A. B by A means what? Input at port A and output at port B. How much power is input at port A? How much power is input at output at port B? So just replacing that values, A and B values. So here this A and B values. So this one will get cancelled in this case. So only remaining will be this one. So that is equals to, again, I get cancelled. So ZL minus ZL divided by ZL plus ZR. Okay. So similarly, finally, we can calculate this power as a voltage, total voltage, that is V0 square divided by 2 into RL divided by Z square. Basically, power is V square by R, right? So here V square is V square by 2R. So here V square is there, so R is here, this is impedance, so it get cancelled with if both are real. So only resistance remains, so only Z remains here. So this equation remains same and it is correct also. So what I mean to say, it is volt square divided by ohms. So that is what you will get here. Okay. So now in the next we'll be discussing about the signal flow graphs using S parameters. So signal flow graph, basically it will tell us that how the signal is propagated from one port to another port and how to analyze those signals. So that we are going to discuss in the next class. Thank you.